right, so whenever we're going to start with inverses, and then we'll go back to composite functions, because inverses are not terribly, terribly bad. Because if you think about what you do to find an inverse, right? Whenever we need to find an inverse, the first thing that we do is we switch our x and y's. So it makes sense that your domain and your range also just switch for that. So the range of a function is the domain of its inverse, and the domain of a function is the range of its inverse. Okay, so it is possible for us to find the inverse of this function that they have given us and then think about domain and range. However, probably whenever I give these to you, I was looking through the test the other day, and the test is going to be calculator active, but it is not going to have Desmos on it. There will be some problems, like for example, when I give you this problem, I will probably include the Desmos graph for the original function. So I will probably include this graph, but it will not be on Desmos. It will not be interactive. Because it's really easy on Desmos for me to just do x equals y minus 3 to the second plus 5. Switch my x and y's. There's my inverse. I could think about domain and range, which is a good tool to use. I'm not saying that we don't want to think about that, but I want you to be able to think about it in several different ways. So if I'm looking at this graph without doing anything to it, so this is, we're looking at domain of f of x and range of f of x. Okay, so our domain for this function, if I look at this function right here, what is my domain? What x values could I have? Negative infinity to positive infinity. So quadratics, they have a domain that's always defined. There's no vertical asymptotes. There's no holes in the graph. There's no like endpoint where it stops, so you won't end up with any issues there. But the range, what is my range for this? 5 to positive infinity. Okay, so we could find the inverse for this and then look at that graph, but you're not going to have Desmos to graph it for you. You're going to find whenever you do this, let's go, I'm going to actually do it, and then we'll tell you why you don't have to actually do it, right? So if I switch the x and y's, I got x equals y minus 3 squared plus 5. So I would subtract that 5 off first. So x minus 5 would equal y minus 3 squared. I would square root both sides. When I do a square root, I am supposed to put a plus or minus in front of it. And then I would subtract that 3. over here. So y would equal -3 plus or minus
Why'd you change
x
the
minus 5.
3 to positive?
Oh,
That's
sorry,
square root.
for no good reason. All right, let's get rid of that negative because that was supposed to be a -3, which means that we should have added 3 to both sides. So we'll have +3 plus or minus the square root of x minus 5. Now, what we're going to see here is actually this is a function that does not have a single function as its inverse because we've got this plus or minus right here. If I graph, I'm going to call it g of x, if I graph 3 plus square root of x minus 5, notice I only get like this portion of the graph, and I would have to do an extra one, 3 minus square root of x minus 5. Also, if you remember function test stuff, you guys remember doing a vertical line test way back in like Math 1? So if a graph, if a vertical line, so if I have like x equals 5 plus, and I'm going to put a slider on that. So like if I do a vertical line here, that is crossing that line twice, so it's technically not a function. So you have to have that plus or minus here, so technically this is not even a function. So many would argue that you have to restrict the domain of this to even have an inverse here. In fact, Coach Wood thinks that maybe on the Math 3 exam they asked a question where they were finding the inverse of a quadratic, which he feels is unjust because the domain should be restricted. So I don't know if that's the case or not, but it's a question to ask. So for this, I could go through all of this and do this part of the work. But then I still have to think about graphing that, which is not the easiest in the world, particularly if you don't have Desmos. You could graph it on your graphing calculator and y equals, but the graphs are a lot harder to see on that than on Desmos. So I could do all of that work, but I don't have to, right? Because I know that if my domain of f of x is -infinity to infinity and my range is 5 to infinity, then my domain for f inverse of x is going to be 5 to infinity, and my range of f inverse of x is going to be -infinity to positive infinity. There. So I may have spent too much time here, but this right here, the work that I did to solve, can be done, but you don't have to do it because the inverse and its function should have just switched domain and ranges for that. What you have to be really careful of is some questions on your test are going to ask you what is the domain of this function. Other questions are going to say what is the domain of the inverse of this function. So you need to make sure you're reading really carefully. So when you see that inverse, because it's probably got the graph of the original function, that you are switching domain and range for that. All right, so domain of the inverse for these. Let's try to do this one without the graph, and then we are going to check it on the graph. So let's just think about f right now. Let's not worry about the inverse. We're not even going to try to find the inverse because we don't have to. So let's think about f. For my domain of f. This is a rational function. The rational function usually looks like this. Okay, so it has those vertical and horizontal asymptotes. So for my domain, what x value is going to be out of the picture I cannot have for my x's? 3, because it can't have 0 in that denominator. Or we can think this has been moved to the right 3, which makes that vertical asymptote at 3. So x cannot equal 3, so that would be negative infinity to 3 and 3 to infinity. So that, using those parentheses, just excludes that one value at 3. Our range of f here, let's think about what number we're not going to get for our range. So that's our horizontal asymptote, right? That y value that we're not going to have. So if that horizontal asymptote, the only way we can change where it's at is to move our graph up or down. What's happened to this particular graph? Up 9. So we're going to have a horizontal asymptote at 9, and you're not going to be able to have 9 as a y value. So this is going to be negative infinity to 9 and 9 to infinity. Let's double check that on Desmos to make sure that that looks good. So if I graph this, f of x equals 4 over x minus 3 plus 9. If I want to be extra sure, I could type in x equals 3. Oh, that is my vertical asymptote. That's beautiful. I could type in y equals 9. There's my horizontal asymptote. That looks beautiful. So that verifies. Probably, I have to look and see. I think I give you the graph of the original function on these. Not one you can interact with, but at least one you can look at. So we cannot have 3 or 9 as our values. So if it's asking me for the domain of the inverse, right, then this is the domain of f, but it's the range of f inverse. It's supposed to be f inverse of x. And this is the range of f, but it's also the domain of f inverse. And this particular problem is asking for domain, so this would be my answer here. Okay, questions? All right. This in particular is a really good one, where it really is helpful to think about the original function first, because your inverse is going to have a restricted domain. So this is one where it's really helpful to think about the f first to get this one right. So let's try it without Desmos, then we'll look at the graph on Desmos. So square root function, it normally looks like this. It's got an endpoint, and then it looks like that. There. Okay. So this particular graph, what's that negative out front do? Flips it upside down. And then what's the minus 4 do? Right 4. So we're looking at this green graph right here is our original. So if you're trying to do this without actually graphing it, that's what we're going to be looking at. And so if I'm thinking of my domain of f, so the original function, okay, what's the absolute lowest value you could plug in? Before. Should I include 4? Yes, because there is a solid dot there. And then it would continue on to infinity. our range of f our range of f we do see we have like a highest value we could have here. What's the lowest value we're going to have? Negative infinity. It keeps going down forever. What's the highest it ever gets? Range is the only time we think about our y-axis. What's the y-coordinate of this point right here? Right, 0. So it goes up to 0. Should I include the 0? Yes. Okay, here. All right, so since we have found domain and range of this one, and let's graph it just to be sure that everything looks good here. And I'll probably give you this graph, but it's going to be beneficial to you if you can figure this out even without the graph, because you need to know what those transformations look like for this test too. So here is our graph. You can see it's similar to what I've got here. 4 is our lowest x value up to infinity. 0 is our highest y value. So everything looks good there. So I don't even have to find the inverse. I'm just going to say the domain of this is now the range of f inverse. And really, did I even have to do that to answer this question? I did not, because it's not asking for range of this, but I like to just do both parts. And this is the domain of f inverse of x, and this problem was asking for domain, so this right here is our answer. So negative infinity to 0. Just real quick, I'm going to show you why it's important that those domains are restricted. So for this function, if I switch my x and y's, I'm going to do this real quick because you don't have to do this to answer this question. If I square both sides, I've got x squared. Oh, wait, no. Let's do this right. Don't square both sides. You got to divide by that -1 first. So negative x equals the square root of y minus 4. I would then square both sides, which is going to give me x squared equals y minus 4. And I'm going to add the 4. So my inverse is x squared plus 4. But if I graph x squared plus 4, does that look like my inverse? I've got like y equals x, this line right here. If I take this black part and reflect it over the x-axis, I wouldn't get this entire red graph, right? What I would get is this graph restricted from 4x is less than or equal to 0. I would get that part of the graph, right? So negative infinity to 0. That domain would be restricted. So for some of these functions, knowing the domain and range is important because it tells you which part of the graph to use. Particularly when you square both sides, you end up with a function where its domain is not correct. Main thing I'm going to do is ask you for domain or range. So I'm not going to ask you to restrict them from the beginning. Or there is a chance, like, I may ask you to find the inverse of something with the restricted domain, and you would just change your x to your y in that as well. So questions here. All right. Try these next two on your own. What kind of, let me address one thing about example 4. what kind of function is number 4? It looks rational. Is it rational? Does it have an x in the bottom? Has to have an x in the bottom to be rational. So what this really is it's just 1/5 x plus 7/5. What is 1/5 x plus 7/5? What kind of? It's linear. So you're just looking at like a slanted line is all you're looking at for that one. Okay, let's look at these. The first one should be pretty easy because what is the domain of a linear function? It is negative infinity to positive infinity. And what is the range of a linear function? If you have just like a slanted line, it's also negative infinity to positive infinity. It doesn't have any holes, any asymptotes. It doesn't stop. It keeps going in both directions each way, both x and y direction. So both domain and range are negative infinity to positive infinity. So the domain of the inverse is also negative infinity. Negative infinity to positive infinity. There. The tricky thing about that one, particularly when you see it on the on like a quiz where everything's mixed together, is recognizing that it's linear because it looks rational whenever it's written the way that it's written. All right. The second one, I put this Desmos graph up here. So let's just talk about f, not f inverse yet. So we're going to talk about the domain of f of x and the range of f of x. All right, so let's see, Lee, what would you say the domain for this function here is? Perfect. Now, question, should I use a bracket or parentheses with my -2? Parentheses, because you have an asymptote there, it doesn't actually include that point. Very good. That is our domain. Liam, what's the range? I think it drops below 1. So, as I look at my y, what's the lowest we see? Like if we were to zoom out, what's the lowest it looks like it's going to go to? It looks like we probably have a horizontal asymptote there at 0. And Monica asked that question also, like, is it ever going to drop below 0? Because we can't tell for sure by looking at the graph. But if you look at the function, it's 1 divided by the square root of x plus 2. Square roots always have to be positive. They can never be negative because you're asking, unless you have like an I or something involved, which for graphs we do not consider. So, so this always has to be positive. So 1 over something is also always going to have to be positive. So it's going to be from 0 to positive infinity for that. And so since we just switched for the inverse, this would also be the domain of f inverse of x, which would be 0 to infinity. I have mostly asked domain for these questions, but if I asked range, you would just circle the other answer there. Okay, questions? All right. Okay. Composite functions are a little more complicated to think about. So before we look at composite, let's go over a few things that I'm going to call problems with domain. Okay, so there are a few things that we have to consider when we're looking for domains of functions, particularly problems like this where we're not going to be able to graph it, and it's asking us for a domain. So, the things that are going to give us trouble with domain are zeros in the denominator, so we cannot have numbers that will give us 0 in a denominator. That's going to give us a vertical asymptote or maybe a hole in the graph depending on what the numerator looks like. All right. We also cannot have negative numbers inside a square root or a 4th root or 6th root or 8th root, but basically you're just going to see square roots here. And we cannot take a log or a natural log of a number that is less than or equal to 0. So I didn't say just negative numbers there because you also cannot take natural log of 0. You can take the square root of 0. So for your denominator, whatever you have cannot equal 0. For square roots, whatever is on the inside right here has to be less than or equal to 0. I'm sorry, greater than or equal to 0. Let me fix that. Greater than or equal to 0 because you have to have a positive or 0 inside of your square root. And for, like, if you have natural log of something right here, then whatever you're taking the natural log of has to be greater than 0. It can't equal 0. And those are the main three things that are going to give us problems with the domain. If a function does not have that stuff, then its domain is just negative infinity to positive infinity. So that is helpful for just domain in general for all functions. Whenever we are looking at domain of composite functions is where we're taking f and plugging it into g, or taking g, plugging it into f. So the domain of f of g of x is the intersection of the domain of g of x and f of g of x. Okay? That word right there, intersection, we can think of it as the overlap. And I'm going to show you what I mean by that here in a minute. And notice that in this case we're talking about f of g of x. So we're going to consider first the domain of g of x, that's your inside function. And then the f of g of x is the total composite. We don't consider f by itself. So you're going to look at the inside function, and then you're going to look at the whole thing when it's put together. All right, so if we are finding the domain of g of f of x, the first thing we have to look at is the domain of g of x. Okay, so our domain of g of x. So there's a lot of different ways you can think about finding this. First of all, g of x is just a quadratic. We should know how to picture a quadratic. No holes, no vertical asymptotes, doesn't end at any particular place. Its domain is negative infinity to positive infinity. Other ways to think about it, it doesn't have any of these problems. It doesn't have a 0 in the denominator because it doesn't have a denominator. It doesn't have negative numbers inside a square root because it doesn't have a square root. And it doesn't give you trouble with logs because it doesn't include a log, right? So the inside function does not have any restrictions on its domain. But when we find f of g of x, we are going to have to take g of x and plug it into this equation. So that is going to be x plus 1 squared minus 4. Oh, I'm remembering why I had those absolute value problems before. Now, that's a complicated function. I don't know what it looks like just off the top of my head. Those are not just normal move up, down, left, right because I've got a square inside of a square root. Those do not cancel each other out because you got this minus 4 over here on the end. So what I need to think about is do I have any of these problems with the domain? Zeros in the denominator I do not have because I do not have a denominator. Logs I don't have to worry about because I don't have a log. But negative numbers inside a square root, I need to think about. Whatever is underneath that square root, is what we call the radicand, the stuff inside of the square root, has to be greater than or equal to 0. So what I'm going to do is I'm going to set this x plus 1 squared minus 4 has to be greater than or equal to 0. So if I want to solve that, I would need to move the 4 over to the other side. So that's greater than or equal to 4. How do I get rid of the square root? I'm going to square root both sides. Now, here is the issue that we run into, which is now reminding me why I had those square root, those solving absolute value problems at the beginning. All right, so normally, if this was an equal sign, I would do this: x plus 1 equals plus or minus 2. Here's the issue. Does it make sense to say greater than or equal to and then put plus or minus 2? You've got greater than 2 or greater than or equal to negative 2. It would just be the negative 2. It doesn't really quite make sense. So that plus or minus only works if you have an equal sign. It'll work for an equal sign. If you have an inequality, what you're going to have to do is this, and this might be new to you right here. You're going to put absolute value of x plus 1 is greater than or equal to 2. So, for this, what that does is when we have absolute value, it can give us a positive. We could have a positive or a negative in there. So it's taking care of that positive or negative. So in Math 3, I think, did Ms. Martin come ask me about these questions? I can't remember for sure. I think solving absolute value equations is in Math 3. You guys were recently in Math 3. Did you do that? I think so. I think it's in 3. If not, it's in 2, but I think it's in 3. So absolute value equations for inequalities, the way that you solve them is you're going to do x plus 1 is greater than or equal to 2. You write it once, basically just dropping the absolute value bars. And then you're going to put, for this one, it's going to be an or, because you have a greater sign. So greater signs, that's an or. If it's a less than sign, it's going to be an and. And then you'll do x plus 1 is less than or equal to negative 2. So what is happening here, if you think about the absolute value, if you think about the numbers that you're going to plug in there that are going to be greater than 2, right? Like if I plug in 1, it would give me 2 exactly. And if I plug in 2 or 3 or 4 or 5 or 6, I'm getting numbers that are bigger than 2. Well, because those absolute value bars like wash away the negatives, on the negative side, you're really thinking about, well, if I get something less than negative 2, once I put the absolute value bars, it would also be greater than or equal to positive 2. All right, so it kind of is our way of getting rid of those absolute values. Because if I plug in something like negative 5, it's going to be negative 4, which when I take the absolute value is greater than or equal to 2. So whenever you're doing these whenever you end up with these absolute value bars right here, you write the first one just exactly like you see it except for no bars. The second one, x plus 1 stays the same. You're going to flip your sign and change the sign of your answer over here. So if I solve each one of those, I get x is greater than or equal to 1. And then if I subtract my 1 over here, I get x is less than or equal to negative 3. So for this problem, your domain, if I think of like a number line here, you first consider your domain of G, which G right here, oh, it wasn't yellow, it's yellow for that. G was negative infinity to positive infinity. That's the whole entire number line, right? Our domain of f of g of x was x is greater than or equal to 1 and x is less than or equal to negative 3. So it would be from negative 3 down and 1 up, right? So you'd have these numbers between negative 3 and 1 that you couldn't plug in. It would give you negatives underneath the square root. So you were looking for where those overlap. So they overlap basically just the same as you have here. So since you had no restrictions for your original function. So our domain of f of g of x would be negative infinity to negative 3. We would use a bracket there because it's or equal to sign. It could actually equal 3. Or 1 to infinity. Okay, questions there? So, G did not offer us any restrictions for this. Basically, I just had to look at what I got when I did f of g of x. But if we look at g of f of x, it's going to be different. Okay? So, for f of x, our domain of f of x, right? That is our inside function for g of f of x. I've got the square root of x minus 4. That is a square root. Whatever is underneath that square root, which in this case is x minus 4, has to be greater than or equal to 0, which tells me that x would have to be greater than or equal to 4. So my domain of f of x would be 4 to infinity. Questions? Now we have to find g of f of x and think about what its domain would look like. So that would be the square root of x minus 4 plus 1 squared. Now, there's not really anything you can do with this. You could distribute it out, like you could write it twice or square, double square. It's really not going to change much about the problem. Does anything cancel out? You cannot cancel the square root and the square because you have this plus 1 over here. If we had the square root of x minus 4 squared, if there was no plus 1 there, then we could cancel the square root and the square. But we cannot because of this plus 1 right here. So basically nothing cancels and nothing really simplifies. So we need to think about problems for our domain. Do we have any denominators? We do not. Do we have any logs? We do not. Do we have any square roots? We do. So we do have a square root. We need to think about what is underneath our square root, which is x minus 4. That must be greater than or equal to 0. We really already did that, right? Because it's this, what is underneath the square root is the same thing as what's underneath the square root for x minus 4. Sometimes things will cancel out and it won't be the same, but it is on this one. So basically we're getting the domain is the same as our domain of f of x. We can't have a 0 in that square root. So our domain for this one for g of f of x would have to be from 4 to infinity. Okay, questions? All right, let's look at some more. All right, we've got f of x is 2x minus 4, g of x is 4 over x plus 3. And they're asking us the same question. This last one, we got to find domain of f of g of x and g of f of x. So let's start on this first one. You got to look at the inside function first, which is, so we're looking for domain of of just g of x. All right, so remember we got 3 things we're looking for. Square roots, logs, denominators. Which one do we have here? Denominator. That denominator, x plus 3, cannot equal 0. So that means x cannot equal negative 3. And we could write that, if we wanted, as negative infinity to 3 and 3 to, that should be a negative 3. Negative infinity to negative 3 and negative 3 to infinity, or you can just write x does not equal 3. There, that is our domain of g. Now we have to consider f of g of x. So f of g of x is going to equal, we're taking g, and we're plugging it in right here for x. So we got 2 times 4 over x plus 3 minus 4. Which you can simplify a little if you want. You could multiply those two together. You'll get 8 over x plus 3 minus 4. We do not have any square roots. We do not have any logs. We do still have a denominator right here. But that denominator is the same as our denominator was for g, right? So we just end up with that same domain as we had for g. So domain of f of g of x would be x cannot equal -3, or we could write it like this, negative infinity to -3, or -3 to infinity, like that. All right, questions? All right, it's going to be different. I think it's interesting that these are different, like when they're composed differently. It's kind of, it doesn't seem like it should be the case. It seems like it should just be the same either way. But so this time, if we're doing g of f of x, we're looking at f of x first. What is our domain of f of x? Negative infinity to positive infinity. We do not have any square roots. We do not have any denominators. We do not have any logs. So we're not having any trouble with that domain. So we're not, if we have any restrictions, it's not going to come from f. It comes from what we get once we plug it into g. So if we plug f into g, we're going to have g of f of x is going to equal 4 over 2x minus 4 plus 3. Which, if I want to simplify that a little bit, I got 4 over 2x minus 1. So again, we're thinking about those three things that give us trouble with the denominator. We're thinking about, do I have any denominators, square roots, or logs? And of course we have a denominator right here. So that denominator cannot equal what? 2x minus 1 cannot equal 0. So if I just solve that like that's an equal sign, 2x cannot equal 1, divide by 2, x cannot equal 1/2. So our domain of g of f of x would be x cannot equal 1/2, or if we want to use interval notation, negative infinity to 1/2, 1/2 to infinity. All right, and we are not going to have, I had one more, didn't I? Yeah. We're not going to have time to do that last one right there. It is similar to 7 there. Your assignment tonight is going to be on Desmos Classroom. So if you go to Desmos Classroom, let me make sure it's assigned. There is one here called Domain of Inverse and Composite. It is a matching problem. So one of these functions, right, one of the cards is going to have the functions on it. You are not going to match it with anything. Okay? So like the domain of f of x would be x is greater than or equal to 3. So for f of x, I'd put that my domain is x is greater than or equal to 3. Some of these you'll be matching like 3 or 4 together, right? So like all real numbers, that's the same as negative infinity to positive infinity. That goes with g of x. You might have another one that ends up there. You might not. But you'll just sort these out. Okay? And it'll tell you how many you've got right on the next one. So try those tonight.